My name is Yi. I'm a research scientist from Intel Labs. I'm here today with my colleague Arun here, as well as my co-speaker. As you see, we have another co-speaker, Tushar, but unfortunately he can't make it due to some emergency in the family. The topic today is rethinking Ceph architecture for disaggregation using NVMe-over-Fabrics. I don't know how many people have just attended the NVMe-Fabrics talk from Sujoy and Mohan. If you guys missed, actually, it's worth to chat with them to get more detail on that. I will touch a little bit more, but focusing more on Ceph as a very popular, successful SDS solution in the era of disaggregation and storage disaggregation particularly. So the agenda for today, we will start doing some kind of a background, a little bit refresher for Ceph. For people who are already familiar with that, that will be kind of a very easy background introduction, as well as the disaggregation in general. And we're going to try to illustrate what the problem is, particularly for Ceph. How do we combine the two? You have a very successful deployment of Ceph. Now you want to introduce disaggregation. How can we solve that problem? And using replication, one of the most common practice, we'll explain the replication flow as well as what we refer to as Datacenter tags when you try to combine the two to provide a good value for your storage services. And based on that, we're going to show, at least based on our observation, the current approaches, as well as our proposed approach. Particularly, Arun is going to take you guys all through the details of the architecture, design, at least the thoughts we have been through in our mind, and what are the architecture detail in the context of Ceph, and how we arrive to our analytical results as some small-scale preliminary kind of evaluation results, and we'll conclude the talk. So this is a very popular picture of Ceph architecture. You can Google this everywhere, but it kind of summarizes the benefits from Ceph being very successful as one of the also default deployment in OpenStack architecture as a block service. It also provides, it's actually an object store, and working together with Swift in the past as well as now. And you can see application would, depending on the storage service you want to provide, you could provide a block level service like your VM, this image, through the thing called RBD, stands for Redos Block Device. Or you want to just to continue using your existing product interface, file system interface. You have a Ceph file system there, then allow you to access it as just read and write as a file. Or you want to just like your image website, you want to just upload your picture just as an object. You have the object interface through the Rados gateway. Underlying is basically by this Rados layer, reliable, autonomic, distributed object store that achieves all these storage service functionalities. It's a software-defined, hardware-agnostic SDS. It basically achieves the purpose of disaggregating your software from your hardware control plane. Then providing the service of everybody who's in storage industry cares about is the reliability of how I can store my data reliably. So they provide replication or real coding if you care very much about your bandwidth savings. And they can replicate, they can rebalance in case of your OSD fails. The details of how Ceph works is in the bottom right, like that block diagram, where the core part is they have a crush algorithm that figures out what is the best way to put your data and where. And that takes into consideration of your network topology, particularly your failure domain, versus your client requirement on your reliability. Like you want a replication, then you could have one pool have two-way replication, another pool have three-way replication. One pool is whatever you favored area coding profile. And they're going to automatically figure out where the data is going to end up to, eventually landing in your storage devices. This one is a little bit background on disaggregation. Disaggregation itself is not exactly new, but there are some new trend in industry particularly making this more appealing. The software-defined storage, as I mentioned, Ceph earlier, is looking at scale-out approach for storage guarantees, and particularly looking at how can I disaggregate software from hardware. And you guys probably already know there are numerous SDS offerings, particularly in cloud storage. It makes it easier to maintain, to manage my commodity-ready hardware with just a SDS stack that I can focus on providing the service that is more related to what client wants. And another angle of the disaggregation is basically separate servers into resource components. So the disaggregation is all about, as I quoted here from the Unix paper, extreme resource modularity, because that provides resource flexibility as well as utilization. That is a direct TCO benefit, and you can see the benefit while deploying your infrastructure. And the deployment flexibility can also provide you, if you want to do a hybrid, you want to do a hyper-converged, that is also possible, because it eventually allows you to scale your storage, or in this case, disaggregation can be storage, networking, as well as compute, scale that side of the resources independently from your application growth. So you have very soft workloads can all fit into the services provided by disaggregation. And particularly, I mentioned that because of industry trend, as I mentioned, the earlier talk from Sujoi and Mohan mentioned the NVMe-over-Fabric. The particularly one appealing factor here is faster interconnect as very well designed standards like NVMe protocol allows you to do very good I/O over to the remote. And that latency make it a very appealing factor for you to say, okay, I really want to have disaggregation there with the faster interconnect, that I can actually manage my resources much more efficiently. Well, as I work for Intel, you notice that I put a picture from Intel, particularly Intel's perspective as rack scale design in the context of disaggregation. And you can see eventually you want to move from today physical aggregation to fabric integration and fully modular resources. The modularity is the key part that allow you to achieve all the benefits you're looking for in your data center infrastructure. So now, Ceph on NVMe-oF, how can we do it? Number one is, so what is the rationale of putting Ceph on NVMe-over-Fabrics? You have one very popular SDS solution as Ceph, backed by the very popular and big open source community, as well as Red Hat. You have the NVMe-over-Fabrics as push in the industry. A lot of vendors come into play, and we can see that both true trends, they're going to somehow merge together. Now we have to figure out how to make them work together and very efficiently, taking advantage from both sides. As I mentioned in earlier one, that the disaggregation is allow you to manage your storage resources independently without worrying about the other side. Now, if you still want to say, I want to use disaggregation, how do you support multiple SDS offerings on disaggregation? All of them is going to say, okay, I own my storage. Even though I'm an SDS, I still own my own storage. They're not designed with a mindset that they are going to be put their data eventually landing on a storage device that is located remotely. And Arun is going to talk about the actual problem you're going to see when you actually start into doing that. So you want to scale compute and storage sets independently, then you have to think about how to solve this problem. And also, this basically opens a door to a lot of optimization opportunities looking at various SDS architectures and where we can do better to take advantage from both sides. Well, by our observations, there are a couple of approaches people have already been kind of practicing. The first one what we refer to as host-based NVMe-over-Fabrics storage backend. Well, this is kind of a extreme of, okay, I want to reuse my NVMe-over-Fabric as just like a SAN. I have mirroring capability. I'll let it maintain my replication. But that if essentially you're saying, okay, Ceph, don't worry about adding up the reliability thing. I'm going to manage that. You have to set up Ceph configuration parameter of saying replication factor 1, because the other side is going to do mirroring. It's an approach, of course. It will work. But the point is, why do you need Ceph to begin with? Now, another option is, I'm a Ceph administrator. I'm very familiar with Ceph. I want to just use as the way it is. Okay, I just don't want to worry about anything related to NVMe-over-Fabric. I'm just going to treat it as a dumb disk. You can still do that. Plug in the NVMe initiator. It's going to bring up a volume showing up in your system. Treat it as a local disk with whatever I/O characteristics you see there. Use that. No problem. You can still have that working. We have tried that. And we actually have a comparison later to that. However, as you can see, essentially the problem is Ceph has a known way, or Ceph, Swift, any others. They want to make sure your service is maintained very well based on your service level requirement from the clients, which basically means how do I know where my failure domain is. By doing that, essentially you're trying to hide that information from Ceph. Ceph cross-map doesn't really know your target distance. There's no such layer in between that the algorithm cares. Algorithm itself is a consistent hashing algorithm. You have to have that topology built in the right mind that actually covers your requirement from that perspective. So it will work. Does it work to the point that we expect it to work? Well, we'll see. Decoupled self-control and data flow is actually what we're trying to after. And we're going to, it's our proposed approach. We're going to talk about that in details later. So as an example, I'm going to focus more on Ceph replication flow. But as I mentioned earlier, SDS reliability guarantees is through the data copies, replication, or redundancy from real coding. The durability, there's via this long-running task called scrubbing in Ceph, or I think Swift is referred as auditing. It's basically make sure your data integrity check can always be successful. If not, there's a certain mechanism to make sure you bring back the right data to the storage device. And we're going to talk about the replication flow, particularly in today's talk. So this picture shows a very high-level simplified flow, about 6 steps. So client's going to try to say, I want to upload my family photo there. This ends up putting a new object in your storage cluster. In this case, you can see there are 3 OSDs deployed, as we refer to as primary, secondary, and tertiary. The primary is going to be say, okay, where are my peers? Where are the secondary and tertiary? Once it's identified through the algorithm, they're going to bring the data from the client, from the primary OSD, then they're going to send that to the secondary as well as tertiary. Once all these 3 pieces of data are actually persisted in your storage device, there will be an acknowledgement sent back. Then there will be actually counter tracking how many acknowledgements I have received. Eventually, I can say, okay, well, good. Your data is placed there according to your rule. Then you're done. This doesn't have the picture of NVMe-over-Fabric. Now, in next, this is where I'm going to show you where what we refer to as data center tags coming from. Recall from earlier slide, the Ceph deployments today is to common to provision separate cluster network for internal traffic, particularly because of the, let me go back one more, the replication traffic between the OSDs. And you have to have a dedicated network for that purpose, as well as for swapping, that kind of task. Now, you do this as what we refer to as stock Ceph deployment right now. This network cost combined as capacity will scale up. And you can see it's almost, in replication case, it's almost a linear factor how it can grow. When you move to disaggregation, this obviously exacerbates the data movement problem. If you follow the arrow from the client, the data block will have to travel to primary OSD. That's a required step 4. But the point is, the OSD is playing a relay role here to pass the data to secondary, tertiary, but eventually just move on to their actual location in a remote target. So that red line is showing as a fabric connection. So the data has really no purpose staying in the primary OSD because it's not going to be eventually resides there. So this is where we refer to as data center attacks, and it's also the focus of our research work to how to reduce them. And the proposed approach, I'm going to have my colleague Arun to talk about more and walk through the architecture details and how we achieve the TCO benefit for Ceph on disaggregation.
Okay, so like Yi mentioned just now, we have these extra hops of the data, so extra bandwidth is consumed, and you have the relay replication, which adds the latency cost. So now let's look at how we could try and resolve or improve the architecture to address these issues. So the first thing, like I said, extra data hops. So what we'd rather do is have data land directly from the primary OSD to the eventual remote storage targets. The issue here, of course, is that we need the final landing destinations. In stock Ceph today, you have a crush map, which provides you the mapping for a particular object, which OSD it should go to. What we are missing is what is the target in this case where you're disaggregating the storage, right? What is the target for each given OSD? So you need extra state, and what we are proposing is to maintain a map of that storage target where you know for a particular OSD where is the remote storage target. Once we have that, the primary OSD can directly land the data to the appropriate storage target. Okay, you did that, but now we have the next issue as to who owns the device blocks. So currently, the owner of the device blocks where the storage event or the data eventually lands is the host file system, or in the newer versions of Ceph, it's BlueStore, right? And if we leave that as it is, and you want to land data directly from the primary OSD, you need to know which blocks to land them to, which means you'll have extra traffic going back and forth between the OSDs to just get to know where to land the data. So to avoid that, what we're proposing is let's move the block ownership to the remote side. So, and I'll talk a lot more in details about that in the next slide. But just to complete the picture, the third part is what we refer to as the control plane. And essentially what we're talking about there is the metadata that's associated with each object. In stock Ceph today, that's tightly coupled with the data. And that's where you have those extra data hops that Yi pointed out in the previous slide, right? So what we are proposing is to say, hey, can we decouple this, have the OSD peers just exchange the metadata or the control traffic, and with just that, can we achieve the end goal of Ceph guarantees that are offered, right? If we are able to do that, we can eliminate essentially n-1, where n is your replication factor, you eliminate n-1 data copies. There's one last bit that remains. You landed the data directly on the remote storage targets from the primary. You send the control messages to the peer OSDs. How do you connect the two? And what we are proposing there is essentially the unique ID associated with each object. We can use that to correlate the metadata with the data. And in typical three-way replication, what you would achieve by doing something like this is what in stock Ceph would take 6 hops. So data from client, first hop, primary OSD to the peer OSDs, the next 2 hops, so 3 hops there, and then each of these OSDs landing the data to the remote storage target, 3 more hops. So you have 6 hops in stock Ceph today, versus if you do it this way, you'll have the data from the client that's we're counting as the first hop, and directly to the remote storage targets, the remaining 3 hops. So that's your 4 hops. So let's go to the next level down about what we are referring to as the control and data plane, and what we are talking of separating here, right? If you look at the Ceph OSD stack, there's actually a clean layering that's already in there, right? So the part we are referring to as control plane is really the object mapping service, right? You get an object, there's a placement algorithm, essentially the crush map, which determines the placement group for a particular object and the pool associated with that, right? So we're referring to those as the control plane. And once the OSD actually gets the object, the details of where the data for that object must be placed on the device, that part is taken care by Blue Stores and the layer below, right? We're referring to that as the data plane. Now, if you're talking about disaggregation, below that you'll have to have an initiator, in our case, NVMe-over-Fabric initiator, talking or sending the data across to the remote storage target. And like we spoke about a couple of slides earlier, this approach is inefficient because you have the relay and the extra data copies, right? So what we're basically saying when we're saying remote block management is to move the Blue Store and have that run standalone on the remote storage target, right? You leave the Ceph top half on the OSD host. You do all the operations that Ceph OSD does today, but you leave the block management, or you move the block management to the remote storage target. And the key part here is the notion of the block ownership mapping table, right? So how do you correlate, given an object ID, where the data blocks are? Now, this is nothing new here. Blue Store already does all of this. It's just where you're running Blue Store, right? On the host versus the remote target. So with these, here's our estimate of what kind of benefits you would get. So the first part, remote block management. The picture on the left is stock Ceph with this pure disaggregated approach using NVMe-over-Fabric, right? And like we mentioned, you have your primary OSD copying the data over to the peer OSDs. And so that's 2 hops, and then the 3 hops down to the target. We're not counting the client data hop because it's common between the 2 approaches. So you have 5 data hops there, and then with our approach or our proposal, the primary will basically be able to send the data directly to the remote storage targets, only control messaging between the peer OSDs. So we have a formula there for interested folks. We can get into the details of that offline. But essentially, I mean, intuitively, you can kind of see we're eliminating the R-1, where R is your replication factor, hops of the data between the peer OSDs. And just to give some more context, for 3-way replication, that would translate to about a 40% reduction in bandwidth consumption. Yeah, so that's about the bandwidth benefits. How about the latency benefits? So what I'm showing here is a sequence chart. And again, let's go from left to right. Each column there is showing what happens at each of the entities involved, right? The client, the primary OSD, and its related primary target. And similarly for the replica OSDs, right? So in stock Ceph today, the data comes in, the primary has to hop that or relay that over to your peer OSDs, and then the peer OSDs, or each of the OSDs will essentially write the data at the remote target. Contrast that with the new approach we are looking at. And the key point to take away really is that we are sending the data concurrently. So from the primary OSD, if the primary OSD knows where the eventual storage target is, you can send that at the same time to all of those targets. And at that same time, you can send it to the control data to the peer OSDs. And so obviously, you don't incur the latency from the relaying that you incur with stock Ceph. Now, there is the aspect of the primary having to keep track and make sure that the data was landed correctly at each of the, the storage targets, as well as the peer OSDs. So just like stock Ceph today keeps a track of counters in terms of making sure the requisite number of replicas were landed, you would need to have some more logic there to make sure was the data landed correctly at the remote storage target, did the metadata land at the peer OSD, etc. But that aside, by doing this concurrent operation, essentially you eliminate, I mean, intuitively, again, I won't go into the details of the equation there, but intuitively, because you eliminate that relay hop, you're essentially removing, the one hop and back of the network transfer, right? And so we estimate that we'll get 1.5x latency improvement by doing that. Okay, so that was at the design level. Here's what we actually went off and tried. So this is a proof of concept, and we started with Ceph Luminous, and the picture here is showing two-way replication. So what we went and modified is in the Ceph object store. So logic was added to essentially do an NVMe-over-Fabric initiator, that functionality in the Ceph object store. And so that is to land the data directly to all the remote storage targets. The other aspect that was modified is in the repop operation, where currently the primary sends the control and data to the peer OSDs. There we just snipped off the data copy part, right? So only the control messages are sent. We're using SPDK, the user space framework for this. So the transport is SPDK RDMA. And on the remote side, we have the SPDK NVMe-over-Fabric target. Now this receives the commands that we're sending from the host side. And we've added an SPDK block device, which takes these commands and essentially does a mapping to make the relevant call to Ceph Blue Store. It's just that instead of happening on the host side, it's happening on the remote target side. Currently, we've implemented this on Soft Rocky, but even as we speak, we're working to kind of do this in a larger scale deployment, but remove Soft Rocky and actually do it on an actual Ceph network. In the picture here, I'm basically showing one part that's highlighted, and that's just to show, in the next slide, I'll be showing some preliminary data that we've got. And so the measurements that I'll talk about are on this, basically the Ceph cluster network. And what we're really measuring is just the received and transmitted bytes. Okay. So in terms of preliminary results and what we did, basically, Rados put was used, and again, we're working towards expanding the set of tests and doing more. But just for this graph and what I'm showing here, so 10 iterations of Rados put, 2 different object sizes, 2 meg and 6 meg, and the picture, like I showed before, we're measuring the received and transmitted bytes on the Ceph network, and as expected. And by the way, this is with two-way replication. So essentially, for stock Ceph with NVMe-over-Fabric, you end up transferring 40 MB per put, and instead, with the approach we are proposing, you basically get about a 48% reduction. And similarly for the larger object size. And again, this might seem a little more than what we had estimated, but I just want to clarify that here we are only talking, or what we're showing is the Ceph network traffic, right? We are not doing anything to reduce any bandwidth consumption on the Fabric side. That remains as is. But just wanted to contrast what's different, right? So that's what we're showing here. And so the initial results, look promising, but we want to expand this and do it at a larger scale. as well measure the latency, for which we'll need to move off of soft Rocky and do it on actual hardware. So yeah, that's essentially what we are going after here. So to summarize, if you use stock Ceph and you try to disaggregate the storage, basically Ceph hasn't been designed for that, right? And because of that, you introduce extra hops and extra relay steps, which we're referring to as the data center tax. And we want to eliminate that by two main ideas: decouple the control and data flow, and do block management remotely. And we want to preserve the Ceph SDS value, right? So all the things that Ceph is great at with respect to reliability, durability, all the operations that it does, we'd like to retain that. And do it in a way where you reduce the TCO for Ceph while bringing the NVMe-over-Fabric value to Ceph deployments, right? So in summary, that's kind of what we are going after. And in terms of next step, I think the first thing is to take this idea to the larger community, and more specifically the Ceph community. We'd like to validate whether our ideas make sense, get more inputs, and make the whole design stronger, if you will. The other thing is integrating the storage target information with the crush map. That would be ideal, as opposed to having two separate places where state is maintained. I already mentioned we'd like to evaluate this performance at scale. The other interesting thing is when you remove the bottom half of Ceph and have that remote, you can actually start looking at or moving towards a vector where you can work with stateless OSDs, if you will. So what we are talking about is if an OSD crashes, you can just quickly failover, get a new instance of an OSD come up, and it can connect to the same remote storage target, and you're back online, right? So that's a nice direction to go after. And the typical question that we get asked when I mention this is, what happens if the remote storage target crashes, right? There, nothing changes with respect to what Ceph does today, right? A particular OSD crashes, you have your peer OSDs figure that out and, take the relevant steps to bring back the number of data copies to the appropriate level, etc. So there, nothing will change, right? So that's what we are referring to here as mechanisms to survive OSD node failures, and we think that's an interesting future area of work. As well, additional offloads that are possible when you kind of do this kind of approach. So I think that's basically what we have here today. And
Thank you.
Thank you all.